Alright, before we actually start talking about three-phase systems and analyzing them, I think it's nice to look at a single-phase three-wire system. And the reason is because this is actually what goes into most households. And now when I say three-wire, we're going to talk about here, you might be thinking three-wire like your three-prong outputs. That's not what I'm referring to as far as the three wires here. We'll talk about that in more detail a little bit here. But basically, if you think about, I'm going to have a box here, and I'm just going to call this is going to be my single phase three wire. And so we have coming off here, I'm going to label this node as A, this node as N, and this node as B. And way that the single phase three wire systems work here is that we assume that VAN is equal to VNB. So it's the same voltage here. So in other words, I could think about this being, I might have 120 volt here, and then 120 volt here. And so then basically, if you think about this, you know, VAB just becomes clearly 2VAN or 2VNB. And so you almost want to think of this, and I used N because you can kind of think of this as, okay, well, this is one kind of hot wire, this is my neutral kind of return, and this is another, quote, hot wire. You know, so we have two hot wires coming in, and then a neutral line. That's not like a three-prong outlet. A three-prong outlet, so if you have a three-prong outlet here, like this, you have hot, a neutral, and I don't know if I have the sides correct here, and then this is earth ground. And so yes, all of your house has, like, basically you have some kind of grounding stake or something in the house. And one of my old houses I lived in, it was like right outside, and it was kind of funny, like you could see where they had just basically driven this giant metal rod into the ground and tied all the wires, all the grounding wires into it. And so, you know, that's where you get the earth ground from. Okay, so if we look here at a kind of a system here, as opposed to looking at it as a box here, we can think of these as having basically two voltage sources here. So this is VAN and this is VNB. So the single phase three wire, I mean, this is circuitry and everything that, you know, we don't necessarily care about per se, but we got two voltages here, and we still have the same label for my nodes here of A, N, and B. But then what we're going to do is we're going to tie these to some loads here. And we'll have a load here of ZP, and then we'll also tie it here and basically to another load, and ZP meaning it has some kind of impedance, might be a combination of resistors, capacitors, and inductors, but we essentially kind of have what looks like two loads, but they're the same, and we tie it together like this. This is a typical single phase three wire circuit. And this would, for instance, this is used well, I shouldn't say everyone, depending on what kind of dryer you have. This is often used in household appliances. For instance, electric dryers are typically single phase 3-wire circuit. Now, if you look at the plugs for like an electric dryer, typically will have 4 prongs. If you look at some really old ones out there, they'll only have 3. And those 3 prongs, of course, correspond directly to those 3 wires that we have in our diagram here. But you'll see ones that have 4 wires. And the 4th wire, you can probably guess what it is that's actually earth ground. So they actually, put an earth ground in there. Okay, so let's talk about, the analysis of this. It's not as difficult as you might think here. If we're wanting to talk about here, for instance, let's talk about what this current is here. And here, let me label these nodes here. We'll call this capital A, capital N, and capital B. And so we'll talk about this as being little ai. Basically, it's the current that's coming up from this VAN voltage source. And then we also have I capital BB, which would be the current flowing through the line right here. Now, we can clearly see here that these two things are connected in parallel. So we know that the voltage across here would simply be VAN, little a n. And similarly, we can see that these two, ZP and VNB, are in parallel as well, so this would be a voltage of VNB here. So just simple Ohm's law, we can see here that I is going to be just VAN, little an, divided by ZP. But then we can also say here that IBB is equal to V and B over ZP. But remember here that VAN is equal to VNB. So IAA is equal to IBB, which then, if I draw one more current line in here and look at what I and capital N is, well, applying Kirchhoff's current law, we know that the current coming into a node, here I'll write it beneath here, so the current going into the node is I little n capital N plus I little a capital A, and that's going to be equal to I little b, capital B little b. But we know that these two things, these are equal. So what we end up getting is that this current on that neutral line there that we've kind of connected here is actually equal to 0. Alright, so when analyzing these circuits, if you're computing currents, this is a really simple case. Right? There's nothing really going on here. It's just, oh, we've got a couple voltages in parallel, we do some Ohm's law and we're done. But let's look at what happens is, what if we include wire impedance? Because in reality, we need to include wire impedance. It might not be very big, but we need to make sure to include it. So let's look at an example here of single phase 3-wire circuit. So let me draw it here, and we're going to analyze this here and see what how we would go about analyzing these circuits. So we have 115 degrees at an angle of 0 degrees, single phase, 3-wire, and then we're going to say that we've got a 1 ohm impedance there, and then my load here is going to look like the following here. Whoops, that's not a straight line. The neutral line will have a 3 ohm impedance. Hundred ohm. 1 ohm. 20 ohm, and then an inductor here, J10 ohm. Okay, now we're not necessarily in the situation above here, so we've got a couple things going on. One here is we don't have shorts here, so we have some load impedance, but then also notice the load here. I don't necessarily have the same load, and I clearly don't have the same load here. I've got a 50 ohm and 100 ohm, and then yeah, there's these components as well that are affecting the overall load, but if I were to measure the impedance here versus the impedance here, I would not get the same value for the impedance. That's not the end of the world, though. We can still analyze the circuit. So let's see, what do we want to do here? We're going to determine the power delivered to each of the 3 loads. And then we're going to also determine power loss in the wires. Alright, so I'm actually not going to go through this here because I don't want, well, I'm going to go through it, I should say. I'm not going to do it in this video. The video is already at 12 minutes here, and I don't want to, this example is going to take a little bit of time with a lot of equations here. So the next video is going to start with this example here. Now, before we do that, let me just kind of identify the 3 loads we're talking about. This is load 1, this is load 2, this is load 3 here. And when I say load 3, it's the combination of both that 20 and J10 ohm. So those are the 3 loads we're talking about. And then the power loss in the lines would be, like, this would be A, B, and then C. Those are my 3 lines that I'm losing power across. Or actually, let's just keep notation same here. So N, B. So we're going to determine the power loss in those lines. So it's not as bad as you might think. We're definitely going to want to employ some of the calculators that we have available to us to solve these problems quickly. But we'll do that in the next video.